Hi everyone, I'm Zixuan Wang, and today I'll be presenting our paper, A Simple Approach to Differentiable Rendering of SDFs. This is a joint work with Xi Deng, Ziyi Zhang, Wenzel Jakob, and Steve Marshner. In forward rendering, we take a set of scene parameters such as the meshes, materials, and lighting as input, and we want to output some rendered image. In differentiable rendering, we are interested in the reverse process of this, which is to compute the gradient of the rendered image with respect to these scene parameters. This can have various downstream applications. For example, here we have some images of the cast shadow of the object, and with the physically based differentiable renderer, we can compute the loss between these reference images and our rendered image, and we can backpropagate the loss through our differentiable renderer to recover the object, although it is not directly depicted in the reference images. More generally, once we're able to compute the correct gradients, we can deform a sphere to some complex shapes, get nearly perfect reconstruction results, and since we're jointly optimizing materials, our reconstruction can easily generalize to new lighting conditions. Now, this all sounds very good, except maybe one thing. A physically based renderer is not so easy to differentiate. To see why, here the ray is initially intersecting with the bunny. And as we perturb the ray, at some point, the ray passes exactly through the silhouette of the bunny. But just as we continue to perturb the bunny slightly, then all of a sudden, the ray changes from intersecting with the bunny to intersecting with the background. And this jump discontinuity is what causes physically based renderers difficult to differentiate. More formally, the outgoing radiance at some point in some direction can be expressed by the rendering equation. And luckily in this talk, we don't need to care about the precise term in this equation, and we can just abbreviate it to a simple integral over the unit sphere domain. Now, differentiating this integral with respect to some scene parameter theta would give us the following if f is a continuous function. But recall that since there are jump discontinuities, we will need a second term to explicitly handle these discontinuities. So here we have the boundary integral that integrates over the set of all discontinuities B, and this equation altogether is generally referred to as the Reynolds transport theorem. In the literature of differentiable rendering, there have been quite many prior works that try to address precisely this problem of discontinuities. And in the ray tracing style approach that we're interested, people either try to explicitly sample the silhouette, which is a boundary sampling approach, or try to circumvent the need to sample the silhouette from the beginning, which is the area sampling approach. In this work, we propose a brand new approach called relaxation, in which we use nearby samples to directly approximate the silhouette and thus enjoy the best of both worlds. The idea of our method is very simple. Directly sampling the silhouette is hard. In fact, the silhouette is a zero measure curve in the 2D plane, so theoretically we have zero probability to directly sample it. But if we relax the silhouette curve to some scene band nearby, and equivalently relax the surface to a scene volume, then it turns out that we can directly and consistently draw samples inside the scene band. To dive deeper into our method, here again we have an exact silhouette point x star, And if we choose to represent our surface as the zero level set of some sign distance function, then for rays that come really close to the surface but essentially miss it, there will be a point on the ray that is the silhouette point of some certain level set. For example, here it is the 0.01 level set, or it can also be the 0.02 level set, and etc. In general, these green points, Y star, are the silhouette point of various level sets, which we call the relaxed silhouette points. We can think of these relaxed silhouette point Y star as a function of the outgoing direction omega. And one thing to note is that the rays leading to these relaxed silhouette points are tangential to some level sets. So these relaxed silhouette points are always some SDF local minimum along the ray, which we will come back to this point very shortly. Next, if we draw a line connecting all these relaxed silhouette points, then we will get this green trajectory. And our goal is to average all the points on this trajectory to approximate X star. Now, if we set the maximum relaxation threshold to be some epsilon level sets, then you might have already noticed that as epsilon gets smaller and smaller, the green trajectory will become more and more like a line segment. And thus, by a first-order approximation, we can approximate this green trajectory as a line segment of length epsilon. So here again, recall the Reynolds transport theorem and the original boundary integral. And with our relaxation just now, we are able to come up this relaxed boundary integral. A couple of things to note here is that in the original boundary integral, the integral domain is over the set of all discontinuities B, whereas in our relaxed boundary integral, we are able to bring the integral domain back to the entire unit sphere. And all that we need to do is to check whether there exists a relaxed silhouette point along the ray, which we can do so by checking if there is an SDF local minimum that is smaller than the threshold epsilon. And this is in fact very easy to do because it is almost a free byproduct during the forward sphere tracing process. So to sum things up, all that we need to do in our method is to first keep track of the SDF local minimums during the forward sphere tracing process. And if we detect some relaxed silhouette point, then we evaluate the relaxed boundary integral using these relaxed silhouette points, add them up, and divide them by a constant factor of epsilon. That's it. Very simple, right? In fact, I want to emphasize a bit more about the simplicity of our method. Our method does not require any additional data structure. It does not require any additional sampling technique or any path guiding. And finally, our method is also very easy to code. So here you see the pseudocode of our algorithm, which at a high level can be stated in just a couple of lines. Okay, so here are some of our results. As you can see, we can reconstruct some complex shapes. And for those of you who care about the numbers, here we use 5112 image resolution rendered at 64 SPP times 10 to 20 views will give us in the end 10 to 20 minutes optimization time ran on a single 3090 GPU. And since our physically based differentiable renderer can jointly optimize materials, we are able to get more complete inverse rendering results. So here again, we use the same rendering setup with a bit more views, 50 views. This leads us to, in the end, 2 to 3 hours optimization times. Although one thing to note here is that we are using a rather conservative setup, which means that there are quite a lot space to further optimize, to further reduce the number of views. In the future, one natural direction is to extend our method to different shapes representations, because our relaxed boundary integral is supposed to work in general, and not just for SDFs. We can also try to jointly reconstruct the camera and lighting for more complete inverse rendering tasks. And of course, in the end, our ultimate goal is to scale this up to scene-level reconstructions on natural images. Thank you.